You know that search bar on your favorite shopping site or streaming service? The one that's just insanely fast? Well, there's a really good chance it's powered by something called Elasticsearch. And today, we're gonna pull back the curtain and see exactly how that magic works.
Seriously, have you ever stopped to think about that? You type, I don't know, red running shoes into a website with millions of products, and bam, before you can even blink, there they are. How on earth does that happen? It feels impossible, right? Well, it's not. And that is exactly the problem Elasticsearch was designed to solve.
All right, so to really get our heads around this, we're going to peel it back layer by layer, just like an onion. First, we'll cover what it is at a high level, then how you actually talk to it. We'll dive into its distributed system, uncover the real secret to its crazy speed, and finally figure out when you should and shouldn't use it.
Okay, let's dive into that first layer. We've got to start with the absolute basics, the building blocks. Before we can get to the cool, complex stuff, you have to understand how Elasticsearch even thinks about data. So the smallest piece of the puzzle is something called a document. And right away, let's get one thing straight. This is not a Word document or a PDF. Nope. In the world of Elasticsearch, a document is just, well, it's a chunk of data, specifically in a format called JSON. The best way to think about it? Imagine it's a single book in a huge library.
Okay, so if a document is one book, what's an index? Simple. It's the whole library. Or, the whole bookstore. It's just a collection of all those related documents. So you might have one index for all your products, a totally separate one for all your user profiles, and maybe another one just for blog posts. Makes sense, right?
And of course, what good is a library without a card catalog? You'd never find anything. Well, that's exactly what a mapping is for Elasticsearch. It's the rulebook, or the schema, that tells the system how to read your documents. It says, hey, this title field, that's text you can search. This price field, that's a number. It's the guide to your data.
All right, our library is all set up. We've got our books, our library building, and our card catalog. But how do we actually get new books in there? And more importantly, how do we find them later? Let's peel back that next layer of the onion and look at the how.
It's actually way less complicated than you might think. Developers interact with it using a pretty simple web API. It's a three-step dance, really. First, you create the index. That's our library. Then, you start adding documents, our books. And when you want to find something, you just send a search request using a special query language that, conveniently, looks a whole lot like the JSON data you put in. And this is where that whole mapping thing we talked about becomes super important. See, when you set up your data, you have to decide how Elasticsearch should treat each piece of information. Two of the most common choices are text and keyword. If you choose text, the system breaks it down. So for the title, The Great Gatsby, it sees The, Great, and Gatsby. That's how you can search for just Great and find the book. But a keyword field, that's treated as one single thing. It's an exact match. Think of a category tag like nonfiction. You want to find that exact tag, not parts of it. It's like searching for the full ISBN number of a book.
Okay, hold on, because this is where things get really, really cool. We've seen the what and the how, but now we get to the why. Why is Elasticsearch so powerful? How can it chew through these insane amounts of data and not even flinch? Let's peel back another layer.
So here's the first big secret, and it's a big one. Elasticsearch isn't actually the search engine, not the core part anyway. It's more like a brilliant conductor of an orchestra. The star musician is a super powerful search library called Apache Lucene. Now, Lucene is an absolute monster at search, but it has one big limitation. It can only run on one computer. Elasticsearch's whole job is to take that amazing power and spread it across a whole fleet of computers, making them all work together.
So how does it do that? How does it manage all that data? Well, it takes a giant index, our library, and breaks it into smaller, more manageable chunks called shards. Think of it like splitting a huge encyclopedia into individual volumes. This lets you store your data across lots of different machines. But what if one of those machines goes down? That's where replicas come in. These are just backup copies of your shards. They're absolutely critical for two reasons. One, for safety. If a machine dies, you don't lose your data. And two, for speed. You can have multiple computers answering search queries at the same time. And inside this cluster, it's not a free-for-all. Different computers or nodes have specific jobs. You've got the master node, which is like the manager of the whole operation and knows where everything is. Then you have the data nodes. These are the heavy lifters. They're the ones actually storing the data shards and doing the hard work of searching. And finally, you have coordinating nodes. They're kind of like the receptionists at the front door. They take your search request, figure out which data nodes need to be involved, and then collect all the answers to give back to you.
Okay, we're almost there. We're at the very center of the onion.
We know Elasticsearch manages Lucene across a bunch of machines, but we still haven't answered the most fundamental question. What makes Lucene, and therefore Elasticsearch, so unbelievably fast? This right here is the magic trick.
So what is this secret sauce? It all comes down to a clever data structure. And it's not just for Elasticsearch. This is the secret behind pretty much all modern search engines. It's called the inverted index.
The concept is so simple, it's actually genius. Think about it. A normal book, you read from front to back. But if you want to find a specific word, what do? You flip to the index at the back, right? That's exactly what an inverted index is. Instead of going through every single document one by one to see if it has the word lazy, the system just looks up lazy in this special index. And boom, it instantly knows. Lazy is in document 12 and document 53. No scanning, no waiting. That's it. That's the core of why it's so fast. But wait, there's more. There's a second trick up its sleeve, especially for things like sorting and filtering. Most traditional databases store data in rows, right? All the info for one product is stored together. Elasticsearch can do something different, something called columnar storage. It groups all the values for a single field together, so all the prices are in one place, all the brand names are in another. So what? Well, imagine you want to sort 1 million products by price. Instead of having to look at 1 million different rows, the system can just look at that one single column of prices. It makes things like sorting and analytics unbelievably fast.
Phew. Okay, that was deep. We went right to the core. So let's zoom all the way back out to the surface. We know how it works now, but what does that mean for you? When should you actually use this thing? What's the so what here?
Well, here's the deal. Elasticsearch is your absolute best friend if you're doing complex, full-text search and you're doing it at a massive scale. It's built for workloads where you do a ton of searching and maybe not quite as much writing or updating data. You also have to be cool with something called eventual consistency, which just means there might be a tiny delay, like a second, before new stuff shows up in search results. And this is the big one. Please remember, it is not a primary database. It's a search engine.
And really, this quote just nails it. If you need to search billions of documents, if you need that powerful full-text search, Elasticsearch is a game changer. But, and this is a big but, if your needs are simple, don't bring a cat into a knife fight. A simple solution, maybe even the search feature already in your database, is probably the right call. It's all about using the right tool for the job. So there you have it. We started with a simple question, how do search bars work so fast? And we ended up deep inside the machine, looking at documents, shards, replicas, and that all-powerful inverted index. We've cracked open the black box. So the question I want to leave you with is, now that you know this secret, what other piece of digital magic are you curious about? What's the next black box you want to open?
Have you ever stopped to really think about what's happening in those few milliseconds after you hit search? It feels like magic, right? Well, today we're going to pull back the curtain and unravel the hidden journey a piece of information takes to go from just data into a result you can find instantly. I mean, you know the feeling. You type something in, hit enter, and bam, the results are just there. It feels completely instantaneous. But how on earth does a system sift through, I don't know, maybe billions of items to find the exact thing you're looking for almost before you've even finished typing? It's kind of wild. Well, a huge part of that magic comes from technologies like Elasticsearch. It's this incredibly powerful open source search engine that was literally designed from the ground up to answer that exact question with just mind-boggling speed. So let's do this. Let's trace the path of a single piece of information and see how it actually pulls it all off. Okay, so our journey starts right at the front door. I mean, it makes sense, right? Before you can search for anything, the system has to even know it exists. So the very first step is adding our piece of information, or what in the world of Elasticsearch is called a document. Now, don't get hung up on that word document. It's not what you're probably thinking, like a PDF or a Word file. Nope. In this world, a document is just a structured bundle of information. A great way to think about it is like a digital index card for a book. You know, it's got the title, the author, the price, the reviews, all that stuff, just neatly organized in one place. So where do all these digital index cards live? Well, they live in something called an index. And you can totally think of an index like a giant digital library shelf, right? All the documents about books go on the books shelf or index. All the movie documents go into the movies index, and so on. It's really just the main way we group similar things together. And getting that document onto the right shelf is surprisingly simple. You're essentially just sending the data over with a really straightforward instruction, basically saying, hey system, take this new book info and pop it into your books collection. That's it. Okay, so we've sent our document, it's left our computer, it's flying through the network, and now it's arriving inside the Elasticsearch system. And believe me, there's a whole welcome committee of different processes just waiting to handle it. See, the document doesn't just get dumped into some random folder. Oh no, it follows a very precise path. First, it hits something called an ingest node. You could think of this like a bouncer at a club. It might clean up the data a bit, or maybe add some extra info. Then it gets passed along to a data node, and its whole job is to find a safe place to actually store it. And only after that data node confirms, yep, it's tucked away safely, do we get the all good message sent back. All right, so our document is officially inside the club, but now it needs a permanent address, right? A system that's got to handle potentially billions of documents needs a super organized filing system to have any hope of staying fast. So let's take a look at how that's all structured. It's all about hierarchy. So you've got your main books index, but that thing could be massive, way too big for a single computer. So what Elasticsearch does is it breaks that index down into smaller, more manageable chunks called shards. And then inside each of those shards, the documents themselves are written into these little files called segments. So if you think about it, it's like library, which is the index, goes to a specific bookshelf, the shard, and then to the individual book, which is the segment. But here is a really, really crucial detail. Once one of those segment files is written to disk, it is never, ever changed. It's what we call immutable. Now that might sound a little strange at first, but trust me, this decision has absolutely massive implications for speed and performance. So if the segments can't be changed, how in the world do you update anything? That's a great question. Well, instead of the old way of finding the data and overwriting it, Elasticsearch does something really clever. It just marks the old document as deleted and then writes a brand new, updated version of it into a completely new segment. The old data is still there, it's just ignored. It's never actually changed.
Okay, so we've seen how a document gets in and where it's stored, but we still haven't really answered the big question, have we? How does all this organization actually lead to that near-instant search we talked about? Well, it is time to reveal the secret sauce. I mean, this really is the multi-billion-dollar question. If you want to find every book that happens to mention the word Gatsby, you can't possibly read through every single document every single time someone searches. Can you imagine how slow that would be? It would be unusable. There has to be a smarter way.
And here it is. This is the inverted index. This is the real aha moment. See, instead of organizing everything by document, the system creates this giant map, a dictionary really, that lists every single unique word and then points to every single document that contains that word. It's exactly like the index at the back of a textbook. So here's the key takeaway. When you search for Gatsby, the system doesn't scan the books at all, not even a little bit. Instead, it does a lightning-fast lookup in that inverted index, finds the word Gatsby, and immediately gets back a list of every document that contains it. This is what turns a painfully slow search problem into a simple, practically instant lookup. All right, we've covered a lot of ground here. We've seen our document arrive at the front door, find a permanent home inside a segment, and get its contents analyzed. So now let's just take a step back and connect all these pieces, because that's where you see why this whole process is so powerful. So here's the entire journey, nutshell version. A simple API call kicks everything off. The document gets processed by a few different nodes, it gets stored away in one of those immutable, unchangeable segments. And, this is the most important part, as it's being stored, its contents are broken down and added to that super powerful inverted index. And that right there is the magic formula. You've got immutability, which makes all the data really easy to cache and incredibly fast to read. You combine that with the inverted index, which makes finding the data basically instant, and what you get is a system that is built for one thing above all else: speed. It's absolutely perfect for any situation where you're searching or reading data way more often than you're changing it. So what we just walked through is the fundamental architecture that powers so much of the modern web. But, it leaves us with a pretty fascinating question to think about. As we all generate more and more complex data, I'm talking images, videos, all this new AI-generated content, how is this whole process of ingesting and indexing gonna have to evolve to keep up? What does the next generation of this look like? What comes next? Have you ever searched for something online and gotten like a million results back?
How in the world does a site like Amazon take that absolute chaos and, in a blink, give you a short, perfectly ordered list of exactly what you are hoping to find? Well, today we're going to pull back the curtain on Elasticsearch to see how it turns that data overload into pure clarity.
So let's start with a classic scenario. Imagine you're on an online bookstore. You type in a pretty general search term and bam, a million results pop up. You know that sinking feeling of being completely overwhelmed? That is the exact problem that a system like Elasticsearch is designed to conquer.
So, how do we even begin to get from this giant sea of a million books to the one you actually want to buy? Well, the very first step is to understand how Elasticsearch even sees the world. It all starts with how it organizes information in the first place. And here's the key idea. To Elasticsearch, everything, and I mean everything, is a document. A book, a user profile, a blog post, you name it. They're all just these flexible containers for data. By treating everything the same way, it creates a kind of universal language to start taming all that complexity. Okay, obviously we don't want all 1 million books. That's totally useless. The first, and maybe the most important step, is to tell the search engine our rules, our criteria, to drastically shrink that list down to something we can actually work with.
And this is our primary tool for the job, filtering. You can think of it like walking up to a librarian and saying, hey, I'm only interested in paperback fiction that was published after 2010. It's the process of applying these really strict, non-negotiable rules to just immediately throw out anything that doesn't fit.
And here's a perfect example of what that looks like in practice. This query is actually asking for two things at the same time. First, it says the title must contain the word great, and then second, we apply a hard filter. The price has to be less than 15. And just like that, our million results might get whittled down to just a few thousand.
All right, let's move on to the next step. We've filtered our list down to a much more manageable size. But right now, it's still just a random pile of relevant books. Now we need to organize them, to put them in an order that actually makes sense to a human being. And that organization is, you guessed it, sorting. This is where we get to decide what we want to see first. Are you looking for the cheapest books, the newest ones, maybe the highest rated? Sorting lets you define the priority and take control. Now, what's really cool here is that sorting can have layers. We're telling Elasticsearch, okay, first, sort everything by price, from lowest to highest. But what happens if two books cost the exact same amount? Well, then we say, use the publication date as a tiebreaker and put the newest ones first. It's super flexible. So, what if you don't actually specify a sort order? Does it just give you a random list? Nope. Elasticsearch has a default, and it's called relevance. It calculates this special number for every single result called the underscore score, which is basically its best guess at how well that document matches what you were looking for. So how does it calculate that magic score? Well, one of the core ideas is a classic method called TF-IDF. It's built on two really simple principles. First, you've got term frequency. A book description that mentions your search term 10 times is probably more relevant than one that only mentions it once. Makes sense. But the second part, inverse document frequency, is where it gets really clever. This gives more weight to rarer words. Think about it. A match on a unique word like Elasticsearch is a much stronger signal than a match on a common word like guide. Together, those two ideas help the engine find the real gems in all that data. Okay, so we've got a filtered list, and it's sorted perfectly. But even after all that hard work, we could still have thousands of results left. We can't just dump all of that on one screen. And this brings us to the final piece of our puzzle, pagination. I mean, seriously, even a very specific search might still give you 100,000 results. Trying to load all of that at once would be incredibly slow. It would be a terrible experience for you, and it would put a huge strain on the server. We need a way to break it all up into bite-sized chunks. Elasticsearch gives us two main ways to do this. The first one, from size, is pretty simple. It's like telling it, skip the first 20 results and give me the next 10. It's great for the first few pages, but it gets really slow if you try to go to, say, page 1000, because the server has to find and then skip all 9,990 previous results every single time. The second method, search after, is way smarter. It uses the last result you saw as a kind of bookmark. It's basically saying, give me the next 10 results after this specific one. This is way more efficient if you're browsing deep into the results. But this brings up a classic, really tricky problem. The data in that bookstore is always changing, right? New books get added, others get deleted.
So what happens if a book that would have been on page 3 gets deleted right after you load page 2? Well, when you click Next, you might accidentally skip over a result that's shifted up to take its place. Not good.
Yeah, this is a huge potential headache for the user experience. So how does Elasticsearch make sure that your view of the bookshelf stays stable and consistent, even when the real bookshelf is constantly being rearranged behind the scenes?
The solution is actually really elegant. It's called a point-in-time search. What it does is it lets you take a snapshot of the entire catalog the very moment you start your search. So for the whole time you're clicking through pages, you're looking at that one frozen, consistent version of the data. Nothing can change out from under you. And the process is pretty straightforward, but it's so powerful. Your browser basically asks for a snapshot and gets back a special ID. Then, for every single page request, page 2, page 3, page 4, it sends that ID back, telling the server, hey, search against that frozen moment in time. This guarantees a stable, predictable experience. And of course, once you're done, you release the snapshot. No more missed results. It's brilliant.
So there you have it. It's these 3 fundamental concepts working together: filtering, sorting, and that smart, consistent pagination that are the pillars that transform a massive, chaotic mess of data into a simple, clean, and elegant search experience.
And this really leaves us with a powerful thought. This ability to create a stable view of a system that's always changing. That's not just about search results. That's a core principle for building almost any reliable application on top of dynamic data. As our tools for managing data and time get better and better, it really makes you wonder, what other digital experiences, things we once considered chaotic or just plain impossible, are now within our reach?
Ever wondered how a search engine can dig through billions of documents and give you the perfect answer in less than a second? It feels like magic, right? But it's not. It's actually some really clever engineering. Today, we're going to pull back the curtain on the technology that powers systems like Elasticsearch and reveal the secrets behind their incredible speed.
Okay, so picture this. You're on a bookstore's website. You type in a keyword, maybe a price range, and an author. And boom, instantly, the results are right there. Now that's not just a nice-to-have feature, it's the solution to a massive data problem. And at the very heart of that solution is a specialized engine working tirelessly behind the scenes.
So what's the secret weapon? Well, for a lot of these systems, including Elasticsearch, it's a high-performance search library called Apache Lucene. You can think of it as the powerful, heavy-lifting engine at the very core of it all.
Here's a good way to think about it. Elasticsearch is kind of like the project manager for a whole cluster of computers. It's handling requests, spreading out the data, making sure everything runs smoothly. But when it actually comes time to find something on any single one of those machines, it hands that job off to its specialist, Lucene. And understanding that relationship is key.
So to really get how this is all so fast, we've got to go a bit deeper. We're going to peel back the layers of this technical onion and see exactly how Lucene organizes data to do what seems impossible.
All right, the first big secret to all this speed, well, it lies in completely rethinking how we store information. It might sound a little backward at first, but trust me, it's the key to everything.
You know, typically you'd think about storing data document by document, right? Document 1 has these words, document 2 has those words, and so on. But to find a single word, you'd have to read every single document. That's just way too slow for what we need. So Lucene does something radical. It flips that whole model on its head. And the way it does this is with a data structure called an inverted index. Now, instead of mapping a document to the words inside it, the inverted index maps every single unique word to a list of all the documents where that word appears. It's basically like the index you'd find at the back of a textbook, but for all of your data.
Yeah, this table shows that flip perfectly. See? On the left, you've got the unique words, we call them terms. And on the right, you have the IDs of every single document where that term shows up. So we're not scanning documents anymore, we're just looking up a word in a list.
And here is the magic moment, the big payoff. If we want to find every document with the word lazy in it, we don't scan a thing, we just jump straight to the word lazy in our index and boom, we instantly get the list, document 12 and document 53. It's a direct, instantaneous lookup. This is the fundamental reason why text search feels so immediate.
Okay, great. So we found our books in literally a blink of an eye. But what about sorting? What if we want to sort them by price, from cheapest to most expensive, or by when they were published? If we have to go back and open up each of those documents just to find the price, well, we've just lost all that speed we gained. There has to be another trick up its sleeve, right?
And you bet there is. This is where the second brilliant piece of the puzzle comes in. It's another data structure that works in perfect harmony with the inverted index to solve this whole sorting and aggregation problem. Just take a look at this comparison. On the left, you've got your traditional row store, like in a normal database. All the info for one book is stored together. So to get 10 prices, you've got to read 10 full rows, including a bunch of stuff you don't need. But check out the right side. That's a columnar store. It groups all the values for a single field together. All the prices are in one neat block of memory, all the titles in another.
So here's how that helps us. Once that inverted index gives us our list of document IDs, we don't go back to the full documents, no way. We go directly to the price column and just pull out the prices for those specific IDs. It's super efficient because we're not wasting a single cycle reading data we don't need for the sort.
And you know, in the world of Lucene and Elasticsearch, this clever columnar store has a special name. It's called doc values. It's built for you, automatically, right when your data is indexed. It's just sitting there, ready to go, totally optimized for lightning-fast sorting, faceting, and aggregations.
So let's put it all together. We have our two superstars, the inverted index for finding stuff and doc values for sorting it. Now let's see how they team up to pull off a high-speed search query.
The whole dance is really just a simple three-step move. First, the inverted index instantly finds all the document IDs that match your search. Step 2, the doc value store zips over and efficiently grabs, say, the price for only those IDs. And finally, step 3, the sorted results are sent right back to you. And this all happens in milliseconds. It's pretty incredible.
You know, there's a quote that just perfectly sums up the whole philosophy here. The inverted index and doc values are both just copies of your data, but they're organized in different, very specific ways. We're basically trading a little more disk space for a massive, massive gain in speed. It's a classic trade-off in computer science, and search engines are just a perfect, beautiful example of it in action.
And that really brings us to the big takeaway. This whole idea of creating specialized copies of your data, trading storage for speed. It's not just for search. It is a core principle behind so much of modern technology. You see it in database indexes, in data warehouses, content delivery networks, the list goes on. So the next time you use a piece of software and it just feels impossibly fast, take a second and ask yourself, what clever trade-off, what brilliant little data structure is hiding under the hood making all of this possible? Have you ever stopped to wonder what actually happens to a single piece of data inside a huge system like Elasticsearch? Well, today we're going to follow that exact journey. We're going to track it from the moment it's created to the split second it's found in a search. Welcome to the secret life of data. So let's start with the big question. How do applications, search through literally billions of items in an instant? I mean, seriously, think about it. You're on a shopping site, you type something in the search bar, and bam, the results are just there. It feels like magic, right? How is that even possible?
Well, that magic definitely has a name, Elasticsearch. It's this incredibly powerful open source search engine that has become the absolute backbone for countless apps you probably use every day. And to make this all super clear, we're going to walk through it all using a simple bookstore example.
All right, first things first. The most basic building block is the document. Now, in the Elasticsearch world, this isn't like a Word doc or a PDF. It's just a structured bit of text, a JSON object for all you tech-savvy folks out there that represents one single thing. So for our bookstore, each individual book, with its title, author, price, all that stuff, that's one document. Okay, so where do we put all these book documents? Well, we gather them up and put them into an index. An index is really just a collection of similar documents that we want to be able to search through. You can think of it as our entire books catalog. It's the big, searchable library where all our book documents get to live.
All right, we've got the basic concepts down. Now let's really start the journey. First up, ingesting your data. How does a brand new book actually get into our digital bookstore? From the outside looking in, it looks incredibly simple. All you do is make one API call, sending the data for our new book over to the Elasticsearch cluster. Just one command, and the whole journey kicks off. But, and this is a big but, don't let that simplicity fool you.
Because under the hood, there's this beautifully choreographed dance happening. First, that document hits what's called an ingest node. Think of it like a bouncer at a club who can clean up the data or add some info before letting it in. Then it gets passed to the right data node. And this is where the real work happens. The node indexes the document, which is what makes it searchable, and then it sends a little confirmation back saying, yep, got it. It's like a super efficient assembly line for your data.
Okay, so the book is officially in the system. But where does it actually live? Well, that brings us to our next stop on the tour. Getting organized, or how Elasticsearch stores all this data so it can handle massive scale.
See, a giant books index isn't just one huge file. That would be way too slow. Instead, Elasticsearch is smart about it. It breaks the index into smaller, more manageable pieces called shards. And to make sure our bookstore never goes down, each one of these shards can have copies, which we call replicas. This is huge. It means if one server goes down, another replica can just jump in and take its place instantly. No downtime for your users.
So what's the magic inside each and every one of these shards? Well, it's a super powerful search library called Apache Lucene. Here's a good way to think about it. Elasticsearch is like the brilliant conductor of a huge orchestra. It manages everything, tells everyone what to do. But Lucene? Lucene is the virtuoso musician, the star player in every section, the one who's actually playing the notes and doing the real heavy lifting of the search.
So what's Lucene's secret weapon? How does it find stuff so ridiculously fast? Well, the answer lies in this brilliantly simple, yet incredibly powerful, data structure called the inverted index.
And this right here, this is the secret sauce. Instead of reading through every single book on the shelf to find a word, an inverted index works like the index at the back of a textbook. It maps every single word to a list of the documents that contain it. So if you search for the word lazy, it doesn't scan everything. It just looks up lazy in the index and instantly knows, oh, that's in Doc 12 and Doc 53. It's a direct lookup, not a slow, painful scan. This is the reason search is so fast.
So we've stored our data in this hyper-organized way. Now for the payoff, actually finding it. This brings us to the final leg of our data's journey, the search quest. Let's look at the anatomy of a query.
So when you search for a book, your request hits a coordinating node, which acts kind of like an air traffic controller for your search. It figures out the most efficient route for your query and then broadcasts it to all the relevant data nodes all at once. Each node's little Lucene engine does its part of the search, and then the coordinating node gathers up all those partial results, merges them together, and sends that final sorted list back to you. It's this massive team effort, and it all happens in milliseconds.
But how does it decide which book is the most relevant and should be at the top of the list? Well, the logic is actually pretty intuitive. As this quote gets at, Elasticsearch figures that a document is probably more relevant if your search term shows up in it a bunch of times. And it gives extra points to rarer words. I mean, searching for a specific term like Elasticsearch is way more meaningful than searching for the word the, right? Because the is everywhere. It's all just a smart statistical way to find the best possible match.
So, we've seen the whole journey, right? From ingestion to storage to search. But the big question is, what does this all mean for you? When should you actually use this incredibly powerful tool? Let's get into the practical takeaways, your playbook.
Okay, here's the bottom line. You should reach for Elasticsearch when you have really complex search needs, like full text search, searching on a map, or even using fancy AI vectors. It's also perfect when you're dealing with billions of documents that get read a lot more than they get written. But on the flip side, if your search needs are pretty simple, or if you absolutely need your data to be perfectly, instantly consistent, Elasticsearch might just be overkill.
And if you want to really succeed with Elasticsearch, these are the golden rules. First, and this is a big one, it is not your primary database. Think of it as a super fast search index that sits on top of your main data. Second, you have to be cool with your data being maybe a split second out of date. We call that eventual consistency. Third, for best performance, you want to keep your data flat, a concept called denormalization. And finally, and maybe most importantly, always ask yourself, do I really need all this power, or is there a simpler solution that's good enough?
And there you have it. The journey is complete. We've pulled back the curtain and seen how data gets ingested, stored, and then found with just incredible speed. So now that you know the secret behind lightning-fast search, what amazing thing are you going to build with it?
ご覧いただきありがとうございます。